with you about Oracle machine learning, an overview, and we'll even talk about some futures as well, what's coming up in the 2020 year. So again, my name is Mark Hornick, Senior Director of Product Management. Our standard safe harbor statement, the following content is intended to outline our general product direction. I'm sure you've seen this many times before. So let's get started with Oracle Machine Learning key attributes. We have 3 key attributes that we'll focus on today: automated, scalable, and production ready. Notion with data science and machine learning in particular is that there's a lot of, let's call it grunt work, that has to get done, anything from data preparation to model building and evaluation. And what we'd like to do is take much of that process and automate wherever possible. And that allows not only data scientists, but other users to get better results faster with less effort. And the non-expert users can leverage machine learning almost just as easily. Now, in the case of data volumes, we all know that data keeps increasing. We get more of it. We have not only the data that's in the enterprise, but we have supplemental data that's coming from third parties, whether it be weather data or social media data. And how do we handle those big data volumes? Well, one way is to provide algorithms and tools that operate in a parallel distributed fashion. And so at this level, we're able to build models, we're able to process data at scale. Another aspect to this is the need or avoidance of moving data. When you have to move large volumes of data, it inherently takes time, and there's additional complexity there. And that can significantly impact the scalability of a given solution. Now, even the best machine learning efforts and data science projects can run into trouble when it comes to getting their results into production. How do you deploy and further update, maintain your data science solutions? Well, to have a production-ready infrastructure that will allow you to get those solutions into production faster, you can do that if your machine learning tools are integrated in a broader platform. And so we'll be exploring these 3 areas and others in this presentation, with the end goal of increasing productivity for users in the enterprise, allowing us to achieve enterprise goals faster and more effectively. And with the time left over, innovate more, spend time on the value add aspects as opposed to just getting the process right. Now, recently, we've rebranded our machine learning capabilities at Oracle, especially with Oracle Database. So you might have heard of Oracle Advanced Analytics, or the R Advanced Analytics for Hadoop, Oracle R Enterprise. Well, we've provided this umbrella term of Oracle Machine Learning, representing our product family or platform. And so it consists of APIs for 3 popular data science languages: SQL, R, and coming soon Python. And we'll actually say more about Python in this session, so you get introduced to that. OML notebooks using Apache Zeppelin to interface with autonomous database, and I'll give you some introduction to what those capabilities are. With Oracle Data Miner, it's a SQL developer extension that provides essentially a code-free environment for doing machine learning, producing analytical workflows. And for the big data side, we have OML for Spark, which is based on our advanced analytics for Hadoop. Now, AutoML Microservices is something that is new to the mix, in that we've made it available for internal Oracle applications, supporting cognitive image and text and scoring and deployment and whatnot. But it was successful with our internal applications, and so we wanted to make it generally available, and that's something that will be coming soon as well. Now, the Oracle machine learning tools straddle both the on-premise side as well as the cloud side. And so we'll be saying more about that as we go forward. But before we do that, let's look at enterprise users and how Oracle Machine Learning empowers enterprise users, such as data scientists, business and data analysts, DBA and IT professionals, application and dashboard developers, and of course, executives. If we look to data scientists, what is it that they really need from an environment, from a platform to be effective in their work? Well, one is data scientists want to use the popular data science languages. So most notably today, we see Python, R, and of course SQL for data manipulation. And the open source environments also have a very rich ecosystem for third-party packages that can address many of the techniques, algorithms, visualizations that data scientists want to use. However, with larger data volumes, we do have to address the scalability and performance implications. And data scientists don't want to sit around waiting for models to build or for scoring to take place or getting their solutions into production. So having an infrastructure that enables scalability and performance is key. Now, we had talked about automation earlier, and wherever we can automate sort of the routine tasks of the data science and machine learning process, we can enhance user productivity. And this is going to be key as we see in later portions of this presentation. Data scientists don't operate in a vacuum, right? They need to interact with the other roles in the enterprise. And so being able to collaborate with business analysts and data analysts and get their results out to application and dashboard developers easily and access the data that the DBA and IT professionals have access to is really crucial. And so we want to provide tools that enable that collaboration and give them access to the data that exists throughout the enterprise and beyond. Now, business and data analysts, of course, have a rich set of tools that they can use. And more so, they're starting to expand into the machine learning space. However, not all users are experts in machine learning. And so for those non-expert machine learning users, we want to provide automation. And one of the components that I'll talk about later, AutoML, will do just that. And that allows them to leverage their domain knowledge and get better results while using machine learning capabilities. And of course, they want to be able to uptake the data scientists' results, collaborating with them and the other users in the environment. DBAs and IT professionals, well, one of their goals is to ensure that the organization gets greater value out of their Oracle investment. Scalability and performance to support data scientists and application and dashboard developers. Having a simpler and streamlined infrastructure, especially as you've heard with the Oracle Autonomous Database, we're able to have many of the routine tasks automated and giving the DBAs and IT professionals more time to do other more value add activities. In particular, perhaps, not only will they be using SQL, but also expanding their skill sets into Python and R, which will now be readily available to them from the Oracle database platform. They also need to be able to leverage database and big data sources and provide easy access to the various users within the organization. Now, if we look at application and dashboard developers, they want to realize intelligent solutions faster. And one of the ways to do that is when you have a machine learning infrastructure that is integrated into the entire Oracle stack. So it's easy to uptake data scientists' R and Python and even SQL scripts and rapidly deploy them. Because if the data scientist spent a lot of time developing a really excellent solution involving an R or Python open source package even, you don't want to have to recode that in some other language or have some other mechanism to have the application or dashboard leverage that. And you can embed these machine learning results through APIs like SQL and REST. And we'll see an example of that shortly. Now, business executives, of course, they want to benefit from the world-class data management and technology and support that Oracle offers, and provide machine learning across the enterprise, because the more people who have access to these powerful tools, they can start analyzing their data for better data-driven decisions themselves. And of course, that rolls up to the executives in the organization. And being able to deploy solutions faster also allows them to realize their return on investment. So when we look at the cross-platform machine learning capabilities, we're going to examine a few areas here, just how these various pieces tie together. And at our next session, Wes Pritchard is going to go into even more detail of how these relate. But for the moment, we'll say we have multiple user interfaces and APIs available. So with user interfaces, we've got notebooks, SQL Developer, Popular R, and Python IDEs like RStudio or perhaps PyCharm or Jupyter. With OCI Data Science, they are a Python-based Jupyter Lab interface. And so they'll be able to tie into our new Python API. With Oracle Analytics Cloud, dashboarding and reporting, also working with the same machine learning capabilities. Now for APIs, we talked about SQL, R, and Python as the programming languages for data science, but we also have REST APIs that are available for cloud application development. Now from the database side, of course, there's the on-premise Oracle database, there's database as a service offerings, and of course then the Oracle autonomous database, which consists of the autonomous data warehouse and transaction processing. So in these tools, we have in database machine learning algorithms, and we can reach out to sources in the data lake through tools like Oracle Cloud SQL and Oracle Big Data SQL. So whether we have other databases, object storage, Amazon S3, and big data service resources as well, we can tie into those and access them as though they were local tables, doing aggregation, filtering, other data preparation that can be combined with data that reside in the Oracle database for machine learning at that point. However, it is quite possible that all of the data you want to work with is in the data lake. And so for that, we provide OML for Spark, which it gives us an R interface and powerful algorithms directly in the big data environment, so that you can prepare your data, you can build models and score data in that environment. Now we've talked about machine learning algorithms. This is kind of a union of all of the algorithms that we're providing with Oracle Machine Learning. You see, we can support a range of use cases. There's the techniques for classification, regression, clustering, attribute importance, association rules. And there are various algorithms that are supporting each of these. Each algorithm has unique qualities, and they process data, they extract rules in a different way and have different insight that are offered into the data. Now, with Oracle Database, we also have SQL analytics capabilities like windows, patterns, and aggregates. Text mining support, we can actually combine data that is unstructured, say a column of data, and automatically extract the tokens, the terms from that, TF-IDF, and combine that with the structured data. And this is built in with the algorithm. So part of this automation that I'm referring to. R and Python packages. So we'll be talking about how we can leverage third-party packages in combination to further extend the suite that we're providing here. So let's take a look at the Oracle Machine Learning notebooks. Now, Autonomous Database, of course, is a data platform, but we're further expanding that as a data science platform. Provides a collaborative UI, as we said, based on Apache Zeppelin, supporting the wide range of users in our ecosystem. But it allows for easy sharing of notebooks, so that say if you had multiple users opening the same notebook, changes made by one user can immediately be seen by the other users. So this really facilitates working together to solve business problems. And these can then be produced as templates that you can access later to share with others in the organization. And you have the ability to specify permissions, versioning, and scheduling of jobs as well. So if you have a solution that you want to run periodically, every night, once a week, those can be scheduled within the tool. This is all included with Autonomous Database, so it's automatically provisioned, managed, and backed up. And we're providing access to all of the in-database SQL algorithms and analytic functions. And soon this will be augmented with Python and R, but I'll say more about that towards the end. So what I'd like to do is show you a brief demo of the autonomous database. We're going to be logging in with the user 20 login. And you see when we come to this screen, we have notebooks, jobs, examples. We're going to go into some notebooks. We can, of course, create new notebooks. We can import notebooks from other users or ones that we've saved ourselves. But let's look at forecasting sales. So as we get into this, we're going to be forecasting sales using an exponential smoothing algorithm for time series data. And we can identify how we'd like to connect to the database for priorities with low, medium, or high through a setting of interpreter bindings. To get started with this example, we're first going to drop the model because our models are first-class objects in the database. And we're going to have the model called ESM Sales Forecast 1. We'll then create a view for the data that we wish to use for modeling. And that's going to be from the sales history data. We have a timestamp ID, we have an amount sold, and that's what we're going to use for this time series example. Now to build the model, we can specify that through SQL because the notebook environment so far is supporting the SQL language, and that will be extended to R and Python going forward. But we have a variety of settings that we can have to the model, the hyperparameters, if you will. And then we'll go ahead and invoke the create model 2 function. So we'll provide a model name that we'd like to use for our first class model object in the database, ESM Sales Forecast 1. That the mining function is time series. The data query that we're providing is from the ESM SH data, the hyperparameters that we specified earlier, as well as the case ID and target. So our model's already built, so we can take a look at what were the settings that the model actually used for this. So it will take what has been provided, and there are other settings that if you didn't specify them, it will choose intelligent defaults. We can then look at the global diagnostics and model quality aspects through the DM dollar view that you see here from the select statement. Now, if we want to look at the predictions themselves, the forecasts, we can do that using the DM dollar VP view that you see here. We view that. We have the actual sold, of course, the forecast for the 4 points that we wanted, and the confidence bounds, both the lower and upper. Now, to visualize this using the Zeppelin native capabilities, we can simply execute a similar query and then look at the results in the visualization. We can specify this through keys and various values to plot the data. So that's a very quick overview of the notebook environment. So let's turn our attention to Oracle Machine Learning for SQL in a little more detail. So, of course, the goal of this is to empower SQL users with immediate access to machine learning in both Oracle Database and Autonomous Database. Now, we've said that we have in-database parallel distributed algorithms, right? That's very important for achieving scalability and performance. But the models are first-class database objects. So that means that you can assign permissions to them. You can find out which models exist in this environment, importing and exporting models across databases, doing a batch and real-time scoring. One of the questions we had submitted early was about real-time scoring. So I'll show you an example of doing singleton scoring with a model from SQL in a moment. Because predictions are no longer considered reasonable if they're just black box, we need explanatory predictive details. For various regulatory reasons, you can't just say a person is denied, say, credit. You have to explain why they were denied credit. And so your models have to have those predictive details available with scoring. And of course, you can leverage this across the Oracle stack because it's SQL-based. Most things within this environment have access to SQL right away. Now, we've already seen how to build a model, and we did the time series model. This is one for classification where we wish to predict from the customer insurance lifetime value table who's likely to buy insurance. And the target column is whether or not the person will buy insurance. So from the real-time scoring standpoint, or what we can also call singleton scoring, we select the prediction probability using the model name. The buy insurance one is now a first-class object in the database, so we can reference it as such. We want to predict yes, that the customer is going to buy, using the values, the predictors that we have specified directly in the query. So by executing this query, we see that this particular customer has a 93% chance of buying insurance. And this model exists in the database, and the prediction takes place in the database. And we can simply execute a query to achieve that. Another interface is Oracle Data Miner. It's allowing you to create analytical workflows, and it supports largely the citizen data scientists, although data scientists and other users have found it to be quite effective as a SQL developer extension for Oracle Database, because it automates a lot of the data science steps. So whether you want to build multiple models in one node, or if you wish to evaluate those models, it will do a lot of that processing for you automatically. It has an easy drag and drop interface, so the nodes on the right-hand side can be drawn on the canvas, and connecting those nodes to form the analytical workflows, which can then be shared. You can export them and import them for sharing with other users. And the wide range of algorithms and data transformations are provided to support your machine learning needs. When you get finished, you can generate SQL code for immediate deployment. And this can be incorporated into applications for doing the entire workflow that has been designed. So let's turn our attention to external tools that require data and what some of the issues are that we encounter. So we have the data source. We could call it Oracle Database or some other tool, and environments like R or Python, Excel, or some other third-party analytic engine. Well, traditionally, flat files have been the mechanism for getting data into these tools. We request an extract, say, from our DBA or from the IT organization, and we have to import that into our tools, and all that data has to fit. But if we don't like the data that we got, we might have to go back and request a different set. So we don't have immediate access to that. Now, some users may have the fortunate access to the database directly. So connectivity packages from R, maybe it's R Oracle or R JDBC, Python, CX Oracle to, say, the Oracle database. But when you have this solution here, how are you going to manage getting this into production as well? Do you have to manually spawn the R Python engines? How do you deal with the scripts and the objects that are being produced? If you're generating models, where do those exist? How do we deal with a number of other issues like the access latency, just to pull the data into these other environments? Maybe there's a paradigm shift from R and Python to some other language and back, which may or may not be convenient for the user. We talk about memory limitations. Well, these tools typically require the data to be fully loaded in order to operate on them. If the data is too large for available memory, you have to take other approaches, which could mean sampling that data outside of the tool. And then you still have to have enough memory left over to process, to do the type of analysis that you want. Even if you have a powerful desktop machine or analytics machine, many of the packages and the environments themselves are single-threaded. They can't take advantage of parallelism. So that's going to limit your scalability and performance. We've already mentioned sort of backup recovery and security. When you have a lot of moving parts, it's more difficult to keep track of all of this. And then getting it into production often results in custom approaches for each project, because there isn't a common infrastructure to support that. So enter Oracle Machine Learning for R and Python. These are two APIs. R is available today with Oracle Database. Python will be coming soon. And both are coming soon to the Oracle Autonomous Database. Well, these interfaces empower data scientists to work with data at scale. And other users are in Python users as well. The idea here is that we're taking the Oracle database and leveraging it as a high performance compute environment. So by having proxies for tables and views in Oracle database, we can manipulate that data from a native R and Python interface by having overloaded a select set of functions to perform those operations on the database server. We also have access to the in-database algorithms. So we're not pulling data out to a third-party engine. We're actually building those models on the data in the database and keeping the models themselves there. Now, when we have R and Python scripts, those scripts can be stored and managed within Oracle Database. And the objects that you produce, whether they be models or visualizations or other objects, those can all be stored in the database. So you have a central repository for managing those. No more, hundreds or thousands of files that have to be managed as part of a solution. These results can then be easily integrated into applications and dashboards through a SQL interface. And we'll see an example of that shortly. With this, we're able to leverage third-party packages so that one of the features that I'll go through an example with is embedded execution. You can actually include third-party packages with your user-defined R functions and have those incorporated into the solution. So the key functional areas of the transparency layer, machine learning algorithms, embedded execution, and with AutoML for Pi, automated machine learning, we're going to look at next. Now, when we look at the transparency layer, one of the benefits of leveraging Oracle Database as the high-performance compute engine is the ability to take advantage of powerful indexing, query optimization, parallelism, and partitioning that is all part of the database infrastructure. So if we have, say, a pandas data frame, and right now we're just going to focus on the Python API. One, it's new, and two, we have very similar functionality available in R, which has been around now for close to 10 years. So we have a pandas data frame, and we can say we'd like to name the table in the database Boston. So we say oml.create. We get back a proxy object for that data. Now, if the table already exists in the database, we can sync that and get a proxy object there. Now, once we have one of these proxy objects, we can invoke overloaded functions like shape. What are the dimensions of this table? Or compute statistics, the standard deviation or skew. Or perhaps we want to use standard Python syntax with the split function to get back a train and test data sets from our original proxy object. But note also that these results, train and test, themselves are proxy objects because we don't want to pull the data back to the client. We want to operate on it in place. And many of the results that we return will be proxy objects themselves. So let's take a look at the in-database modeling. And in this case, we're going to focus on support vector machine. So we have the OML package. We're going to import SVM. We'll get our proxy object for a table called onTime_s, which contains flight information. And we want to look for some anomalies in that data. So we might specify an outlier rate of 1%. We want a linear kernel. And then we're going to fit that model using the data onTime_s, which of course is a proxy. So if we look on the right, we have Oracle Database, which has the data. It has the algorithm, and the model is being produced in the database. Now, if we want to look at that model, we can interrogate the various views for that, or view the model itself as a Python object. But you did not have to move any data into the client in order for this to take place. So embedded execution, I mentioned this earlier. This particular example will highlight parallel execution for a partitioned data flow using a third-party package. You can certainly do things in a non-parallel fashion, but this example shows how parallelism can be applied. Consider the data scientist that wants to build multiple models on different partitions of the database. set. We're looking at the iris data set. It's a popular one that contains measurements of iris flowers from 3 different species. So we're going to build a model in a function called buildLM, and it's going to predict the petal length from the petal width and return that model. It's leveraging the sklearn package, so we have the linear model from that. Because we want to tailor the model to each species, we'll identify an index on the species column. We could have multiple columns involved in partitioning of the data. Then we'll invoke group apply, where the iris data frame proxy object is going to be partitioned according to the index. We're going to invoke the function buildLM on that. Notice we're passing in a function object, but we could also have stored this function in the Python script repository and then invoked it by name. And lastly, how many parallel Python engines we would like to execute this. Now, in the on-premise deployment, we see that Oracle Database is going to be using external processes to spawn the Python engines. It will load the function into it, the data, and the resulting models will still remain in the database. And we can pull those back to the client when we want to look at those. So here's an example of showing the SQL API, where we have a very simple function called random red dots. And this function takes 2 arguments of the number of dots for 2 different scatter plots, and also returns a data frame, a very simple data frame of 2 columns and 10 rows. And we're going to store this function in the Python script repository so we can invoke it by name from SQL. We could just as easily have created this from the Python interface. To get the images, we'll invoke the table function pyqeval, specifying the PNG. And here you can see the images that are being returned directly from SQL Developer. So these could be arbitrarily complex images, visualizations that you've generated using your favorite Python package. Now, if we look at the ability to specify additional arguments, we have the number of dots 1 and 2, and we can incorporate those into the execution, and then we'll get images that are modified accordingly. To get the structured results, we do this by specifying what the shape of the resulting table looks like. So here we're specifying select 1 ID and 1 val to say that we want an ID column and a value column that are numeric. And you see we have the table produced that could be materialized or joined with other data. Now, if you want to get both the structured and unstructured or image content together, we give the option of generating XML. So not only do you have the structured content there, but you have the images in CData, which is a base 64 encoding of the PNG images. So any application or tool that can leverage XML can incorporate both the structured and image results directly. So let's move on to AutoML. As we noted earlier, this is new with OML for Pi, and it's only available with OML for Pi. Its goal is to increase data scientists' productivity and sort of reduce the overall compute time itself. As we go into cloud-based interfaces, reducing compute time is good, certainly from the user's perspective. So what does AutoML do? Well, we have 3 main areas: model selection, feature selection, and hyperparameter tuning. With model selection, we showed earlier that we have a range of classification and regression algorithms. Well, which algorithm should you choose? AutoML works today with the classification regression algorithms only. But if you've got 5, 6, 7 different algorithms to choose from, do you do an exhaustive search, building models on each of them? And do we change the parameters for that? With the auto model selection, we actually are using a technique called meta learning, where we've built a model to guide the machine learning process. So we can recommend which algorithms are most likely appropriate for the data based on the distribution of the various predictors and target. So we produce a best model faster than with exhaustive search. But once you know what algorithm you want, there's also this notion of selecting the features or the predictors that you want to use when building that model, because not all features are useful, and different sets of features may be appropriate for different algorithms. So if we can reduce the number of features by identifying those that are most predictive, we not only improve performance because we're processing less data, but we might also achieve greater accuracy. And I'll show an example of that next. For the hyperparameter tuning, the goal here is, given an algorithm and a set of features, can we tune the hyperparameters in a way that will significantly improve accuracy? And again, we want to avoid the exhaustive search technique. So there's a meta-learning approach here where we're taking a gradient descent, zeroing in on the best hyperparameters to achieve that goal. Now, with this in place, we're not only automating this to increase the data scientist productivity, but think about it from the non-expert user perspective. They can also now leverage machine learning because they don't need to know the details of the individual algorithms and what all the specific parameters for each of those algorithms or hyperparameters refer to. This part of the process is taken care of. Now, does this sort of replace the data scientist? Well, no, because we still have the formulation of the problem, the acquiring and integration of the data, and the preparation of that data before it even gets to this process. And that's really critical as well. But this is a way of overall addressing some of those repetitive tasks that need to be done, and those are readily automated. Now, for feature selection, here's a very simple example. One of the things that Oracle Labs did, this is based on technology from Oracle Labs, is they evaluated a wide range of data sets. And here's just one, 56,000 rows, almost 800 columns. With the feature selection, we were able to achieve a 60% reduction in the number of features and getting an 18% increase in accuracy because we're eliminating noise from the data. And it was like 1.3 times faster to do this using an SVM Gaussian model. So it definitely is a possibility for significant benefits with feature selection. So let's turn our attention to machine learning for Spark on the big data side of things. Now, this is supported by the Oracle R Advanced Analytics for Hadoop component of the big data connectors. And its goal is to leverage the Spark 2 environment for powerful data preparation and machine learning. It can work across the range of data lake sources, many of which we've seen in that earlier slide. We can achieve scalability and performance using the full Hadoop cluster. And this is achieved in part because we have machine learning algorithms that are both native and leveraging the Spark MLlib implementations. And these are all rolled into the same OML for Spark framework. You might notice that the interface here mimics what we've done on the database side. So we have a transparency layer, a set of parallel distributed machine learning algorithms, and a compute framework that enables the data parallel and task parallel execution in combination with open source packages so that you can build advanced solutions leveraging the open source environment. OML for Spark performance is one that certainly is important to users in the big data space. And here's a comparison of the native OML for Spark GLM logistic regression with the Spark MLlib, which is also integrated into this platform. With the native implementation, we see that when the data fits in memory, we're up to 7 times faster than the Spark MLlib algorithm on the same platform. What's interesting is that when the data can't fit in memory, the OML for Spark implementation is still able to solve that even at 10 billion rows. Now, you might not have 10 billion rows that you need to build a model on, but it goes to the underlying architecture and how the algorithms are designed and implemented to even enable such a capability. Moving on to applications, integrating Oracle machine learning. Over the past decade or so, we've worked with various applications groups to incorporate machine learning capabilities, whether it's human capital management, customer relationship management, financial services, spend classification, and more recently, content and experience for unstructured data analytics and integration cloud for digital process automation. I'm going to focus on those last two next, mainly because they tie into the OML microservices, which I want to say a little bit more about. With the integration cloud, it's, we said, focused on data process integration, but it's to help business users make better decisions using machine learning models. And this will increase the automation of human-centric approval workflows. Now, within the Oracle applications, there are a variety of software as a service, process-centric apps that leverage this technology. But what are they using? They're using the Oracle machine learning platform to build models in autonomous database and then deploy them using the microservices. Now, another example, being content and experience, is really cool from the visualization side, where they improve content discoverability. So if you'd like to search or organize your content, or maybe you want to tag images, videos, and text, this is a tool that enables you to do just that. And it's leveraging the OML cognitive microservices, which I'll talk about in a moment. So that brings us to the roadmap for Oracle machine learning. Oracle has really invested a great deal in machine learning ever since it acquired Thinking Machines back in 1999. So basically, over 20 years, we've been incorporating machine learning into Oracle database and the overall Oracle stack. So let's see what we're going to be doing in the coming year. OML microservices. I mentioned that we've made this available to internal Oracle applications teams, but because of the success there, we're going to be making it generally available for other users, customers. And so model management services, whether it's building and deploying models, monitoring the accuracy of models for prediction and predictor drift, indicating basically when should you rebuild your model. Having a model repository to store, version, and compare models. Cognitive services, feature extraction, image and text. And user-defined scripts deployment. So we can take our Python and R user-defined functions that we were using perhaps in the embedded execution case and invoke those through a REST API. Of course, all of these microservices are made available through REST endpoints for ease of application integration. These are just a few examples of the microservices APIs. So if we're dealing with model management, we of course want to find out which models do we have available, can we version them, get back a specific version, model deployment, scoring, and finding out what are the needed parameters for that model to do scoring, cognitive image, image classification, not suitable for work classification, object and face detection, image and face similarity, case of cognitive text, named entity recognition, topic extraction, keywords, sentiment summary, and similarity of documents. So the wide range of things that we'll be making available there. Now, with Oracle Database 20C, we've had a number of frequently requested algorithms, and two that we'll be adding are XGBoost, supporting a range of mining functions, classification, regression, et cetera. And of course, everyone knows probably that XGBoost is a highly popular and powerful algorithm that has been used in Kaggle competitions to win, basically, the best accuracy. So it will be a nice addition to our database suite of tools. Another algorithm is MSET SPRT, and this is based on an Oracle Labs algorithm, and its intent is to support anomaly detection for sensor data. Certainly, IoT data sources are becoming more and more prevalent, and the need to identify where some of the data values could be signaling trouble. Imagine if you have a farm of wind turbines. Each wind turbine has many sensors, and you might want to know exactly what's going on with each one of those. And is there a combination of problems that could result in downtime? And do this across all turbines in a given farm? Well, this is one possible use case. As far as expanding autonomous database with Python and R, we've mentioned that autonomous database grows as a data science platform, and with the OML notebooks, we'll be adding support to extend our SQL interface with Python and R. So that means in the same notebook, you'll be able to include paragraphs of each of the languages. So perhaps you'd like to use SQL for some initial data munging. Maybe you want to use R for some visualization and then Python for model building, or vice versa. So you can combine these in the same document. Of course, your Python and R scripts can be managed in the database, and you'll have access to the scalable execution through the transparency layer and in-database machine learning algorithms. With the OML for Pi, AutoML will be made available here as well. And with the OCI data science, OML for Pi will be integrated there so that you'll be able to reach out from the Python environment provided by Data Science Toolkit into autonomous database and the in-database algorithms. With respect to another interface, we've talked a lot about AutoML, but that was code-based, right? It's going to be Python. And we would like to provide a code-free user interface that supports this automated end-to-end machine learning. So not only do we enhance the productivity of data scientists and the user experience, because they can really get a jump start on producing a model quickly, and then they can see, well, do I need to refine that? Do I need to change some of the parameters or the data and the like? But we can also make that available to non-expert users who can leverage ML for the same reasons that we cited back with the OML for Pi Python interface. But this tool will go a little bit further in supporting the model deployment and monitoring, and also support model management. So in the case of monitoring, we'd like to know, is the model degrading over time? Is its accuracy changing? Is there drift in the prediction or the predictors that are there that we should consider rebuilding the model? So we'll be saying more about that in future sessions. With OML for R and Python, we'll be exposing additional OML for SQL algorithms to R and Python. And we'll be supporting the R and Python releases there as well. Enabling Oracle Database standard integration, installation, patching, upgrade, and downgrade. This will be integrated more seamlessly with that for our on-premise users. With OML for Spark, this is going to be a new cloud-based architecture, and it will support machine learning activities on big data, including model management and cognitive services, deployment and monitoring. And this will be achieved through cloud-oriented packaging focused on containers and REST APIs. And by providing this new architecture, it will make it easier to have a uniform experience across both the database and the big data by providing the same OML for Pi and R interfaces in both environments, so that users can be less aware of where their data actually resides. In the case of algorithms, there will be a number of enhancements there. Neural networks, support vector machine will be a new algorithm added, as well as clustering algorithms. And those are new native algorithms. We already have those with the Spark ML lib. Now, GPUs, of course, are very important in the deep learning space, and so we would like to take advantage of those by enabling GPUs for the in-database algorithms. We'll be replacing MKL with QBLAS. By having GPU shapes available, we can then have our user-defined R and Python functions that might take advantage of packages that can use GPUs like TensorFlow and Keras, have that same performance gain. And because the OML microservices for GPU processing, that will be useful for images, because the algorithms that are there are also deep learning algorithms that support both images and text for a high performance. So wrapping this up, we have the Oracle Machine Learning key attributes. We've talked about how automation is certainly important and critical for a lot of users to help streamline the whole data science machine learning process. The need for dealing with scalable solutions, that you can't really work with enterprise level data unless you have parallel distributed algorithms and infrastructure to support that. And in the case of putting your results into production, having the infrastructure that makes it a seamless process to go from the models into an application or dashboard is certainly a key. So we're looking to increase productivity, achieve enterprise goals, and give you more time to focus on the things that are more innovative and more interesting to solve business problems. For more information, you can go to the oracle.com/go-to/machine learning site. This will bring you to a number of resources for Oracle machine learning. And with that, I thank you for your attention and I'd be happy to entertain any questions.
Thank you very much, Mark. So we've had a few questions here in the chat. I replied to a few. I'm working on one specifically. People asking about OML for Pi, whether it can be used for data on file storage like data lake without the database.
Well, so today, or I should say in the near future, because OML for Pi is not released yet, it is a database capability. So it does require Oracle Autonomous Database or Oracle Database on-premise or Database as a Service. That said, you can reach out to data lake sources through the Cloud SQL and Big Data SQL. In the future, as I mentioned with the OML for Spark, that will have an OML for Pi interface that would allow you to work directly on big data, and that would be without requiring Oracle database. But for the certainly the near term that we're talking about, it will require Oracle database.
Perfect. Also, other questions. Will support for SQL Developer Data Miner continue, or will it be replaced by ADW notebooks, etc.?
Well, the existing Oracle Data Miner will continue in its current form. We will provide maintenance support for that. But our main focus is driven toward the cloud. And we're looking at the AutoML UI and continuing to expand that. What we've shown so far is just sort of scratching the surface of where we'd like to take that. And so that's where we'll be investing our development resources, at least as for the coming year.
Excellent. Also, another question regarding the running the ML processes in the same instance, running the OLTP system. So how is the load managed?
Well, the load will be as you would expect for any load being placed on the system that is supporting it. If you would have to scale your database resources accordingly, as you would a decision support system is what we normally say to those types of issues. I think if you are using open source tools and you want to have a large number of say Python and R instances running on the back end, you'll want to factor that into the amount of compute that you have available, both for the database and for those other engines, because they do interact. They consume resources. Essentially, we're providing an engineering solution with this, and so we have to take into account the realities of the hardware that is available to support what's being demanded of it.
Excellent. Another one that came in is also about if we can export machine learning models in PMML from OML.
Yes. The PMML representation is one that we've explored many years ago, actually, and at this point, the models exist in the kernel of the database, and we leverage those models directly in the database, right? Especially with the OML for SQL, R, and Python. And so exporting them to a separate representation is not something that we have enabled, certainly through PMML. With the microservices, there will be more of a scoring engine type capability that will allow you to use these models outside of the database, but that's something that will be coming when the OML microservices are made available.
Excellent. And I think a great question as well, which might get clarified in the next session even more, but what is the differentiation factor from OML with R and Python versus OCI data science?
Well, I think one of the key differences there is the data science interface is focused on the data scientist. It is looking at having a Python interface only. One of the differentiators is that with the database, we have SQL, Python, and R made available for that. With the data science also, they're targeting more the open source aspect of that, and where data is not necessarily in Oracle database. So if you have data that's in object storage or other representations where you're not planning on putting it into Oracle database, then certainly that would be a natural environment for Python users to take advantage of. They have capabilities for AutoML enabled, and we have that with our Python interface as well. So I think there are definitely synergies between the two, and that's one of the reasons for having the OML for Pi package enabled with the OCI data science, because it will allow those users to leverage some of the capabilities that the data science offering has and go into the autonomous database and get all of the benefits of the in-database modeling and preparation and scalability that OML for Pi is providing.
Excellent. So we are now at the top of the hour. People are asking, 2020 Q3 or Q4? I guess that's related to OML for Spark. So I can speak about that a little later. Yes. Yeah, so OML for Spark will be made available with the Big Data Service probably as soon as we get it done. So as soon as Big Data Service is out, we're going to have some instructions and scripts on how to install OML for Spark in there. And then following that launch, we will work on getting integration with the Oracle data flow as well. All right, so it's the top of the hour. Thank you very much for all the participants, and I see you guys next month. Thank you very much, Mark. Really appreciate it.
Thank you, Marcos, and thanks everyone. Talk to you later. Bye.
Thank you. Bye.